Okay, AP Calculus AB Unit 4, Day 2 lesson. So I'm going to start off with a warm-up. So go ahead and try this first warm-up problem with all these different answers. Should be super quick. We're just looking at the graph and determining answers. These dots, I think, mostly add up to very nice values. Be careful. Some of these are one-sided. Some of these are two-sided limits. Some of them involve a little prime symbol, which would indicate something to do with the derivative. What's the derivative doing? So go ahead and pause the video and try and get all your answers. Should be pretty quick, like I said. And then I'll discuss them together. So go ahead and try it. Okay, assuming you've tried it, the limit as x approaches 0 from both sides has to agree, appears to be approaching 2. Part B is approaching 2 from the left side, which approaches 4. The overall limit at 2 does not exist because the two sides don't agree. The left side's going to 4. The right side's going to 2. So it does not exist. The value, the function at 3 appears to be 3. That does not have to agree with the limit. The value as x approaches 3, both sides agree that it appears to be going to 1. Okay. 4, both sides appear to be approaching 0. So limit will exist at a corner or cusp. G, we're going towards 7 from the left side. Now, technically does not exist, but I want you to write positive infinity. So technically does not exist, but I want you to write that it's going to positive infinity. It describes the behavior. Right side is going to negative infinity, technically does not exist. 11, it appears both sides are going up to 2, even though there's a hole there, even though the function isn't defined there. Now, J is talking about the slope as we approach 0. And the slope on both sides appears to be up 1 over 1, up 1 over 1, appears to be 1, right? As we approach 4, the slope on the left is -1, the slope on the right is something positive. So we're going to say does not exist because the slopes on both sides do not agree, which is always going to happen at a cusp or a corner because they are not differentiable because the two sides don't agree. Okay. 11, as we approach 11, we're going to say does not exist. I would say it appears to be a cusp that has like a vertical tangent. And so just as a note, if we were to take the limit as x approaches 11 from the left side of f prime of x, I would probably say the slope is going to positive infinity. If you were to take the limit as x approaches 11 from the right side of f prime of x, I would say negative infinity. Now, some people might be like, no, that's going up too. No, but this is a negative slope, right? If you're looking at slope and you're thinking left, right, and it's going down, that's a negative slope. So be careful with the slope stuff. So anyways, hopefully that was some good practice. We're going to talk about some new things here. If f of x is continuous, meaning there's no holes or jump or anything like that, then you should just be able to plug in the value. So for instance, as x approaches 3 of 6 of x, you plug 3 in and you get 18. Now it's kind of boring, so probably rare that you'll get something that easy, but the reason that we can do this is because if you were to graph this line, goes through 0, 0, goes up 6 over 1, goes up another 6 over 1, goes up another 6 over 1, to 18. And it's just a line. So if we approach x equals 3 from both sides, and the function actually is connected and exists, and it should just be whatever the value of the function is. The only reason something weird might happen might just be because, if there's a hole in the graph or something like that, then we might have to do some other stuff. Now, that's going to be rare. That you're going to just have a nice, continuous, easy graph. If it's not continuous, well, that's when things get interesting. So you might have, holes, jumps, and what it really comes down to is that you can't draw the graph without picking up your pencil. Kind of a sort of a simple way of describing that. So here's some different examples, and we'll talk about the techniques that we're going to use. As you plug 2 in here, you get 0, 0. So we call this an indeterminate form, meaning you cannot determine the answer. Okay? Is it 0 because 0 divided by anything 0? Is it infinity, undefined, because anything divided by 0 is undefined? Is it just like 1 because they're the same? It could be any of those. So now, what did you guys do last year in pre-calc? In pre-calc, you guys would kind of run into these issues. And what we would do is we'd factor and simplify it. So we would say, oh, well, this equals the limit as x approaches 2 of x minus 2, x plus 2. And then you have x minus 2 here, and you would cancel them out. And then you'd reevaluate, plug 2 in, and you get the answer is 4. And that is actually the answer. Now, why are we allowed to do this? Well, if you were to graph this function, and I could do it on my graphing calculator real quick. Let's take a look at it real quick. So I'm going to do parentheses x squared minus 4 closed divided by parentheses x minus 2 window. I don't know, negative 5, 5, negative 5, 5. We'll just try that real quick. Looks like a line, right? And as you approach 2, it's just approaching whatever value is on that line, which looks around like 4. And by the way, this line is this right here. So it actually looks like this line, this simplified version. It goes through y-intercept of 2, has a slope of up 1 over 1, up 1 over 1. So it looks like this. It behaves. Okay. The graph looks like y equals x plus 2, right? Except at 2, there's actually a hole in the graph. So we could try it right here. This is that graph that looks like a line. You can say, well, let's get the value at 2. Nothing. There's a hole. Now, up until that point, though, the graph, if you're following the graph and you don't know the hole's there, you would say, oh, it looks like it's going to be 4. Okay, so it looks like this line with a hole. Now, it's okay that it has a hole at x equals 2. The limit still exists, and that's why we're able to get rid of the hole in the graph. Okay, I will show you guys some new techniques later on, not today, that would also give you the same result. That's called indeterminate form. One possibility, if it's 0 to 0, is you might be able to factor the hole out. Sometimes there's a hole and you can't factor it out. So here's another example. If we plug 2 in here, we get 8 minus 2 minus 6 over 2 minus 2. And that's 6 minus 6 is 0 over 0. Oh, indeterminate form, right? Maybe there's a hole in the graph. Now we would want to divide it out. Now this is a cubic, so we can't factor that like with our normal techniques. We need to use synthetic division. You do not need rational root theorem. Okay, rational root theorem is a way of getting a list of potential factors. We know this is the guy that we hope to divide out because it should be the one that's causing the hole. So this is easier than when you have to do rational root theorem. We're going to do synthetic division still, which is separate from rational root theorem. We usually use it with rational root theorem just as a nice way. Okay, we know x equals 2 is a root because it cause the bottom goes 0, cause the top goes 0. It has to be a root, right? You know it's going to give you a 0. And so we don't need rational root theorem. Okay? Rational root theorem is just a way to find a root, any root. We got a root. It's got to be x equals 2. So we're going to do synthetic division. It's going to be positive 2 here because that's what it comes from, x minus 2. And we put the coefficients of the original 1, 0, because there's no x squareds, -1, -6. Drop the first number down, multiply by 2, add these guys, multiply by 2, add these guys, multiply by 2, add these guys. You should get 0 at the end if you actually divided an actual root out. If you don't get 0, don't fake it. Figure out what went wrong. Did you forget a missing term? So these are the coefficients of new polynomial 1 degree less than that. So it's 1x squared plus 2x plus 3. And here's the whole. And then we're going to reevaluate, plug 2 in here. It's 4 plus 4 plus 3 is 11. There you go. So you might need some synthetic division every now and then to help you with factoring. This next one gives you 0 over 0 in determinant form. Let's see if we can get the factor the whole out. Now you might be like, well, the top and bottom are already prime, meaning they're already factored. True, but we know that this thing on the bottom that's giving you 0 probably should be able to get one of those out of the top. And when you think of it that way, you think, oh yeah, x could be the square root of x squared minus 2 squared. So we could see it as a difference of squares. And there's a whole. And square root of 4 is 2 plus 2 is 4. Okay, so next one, -3 cubed is -27 plus 27. -3 plus 3 is 0 over 0 in determinant form. Now you should show that before you start trying to factor out wholes. We don't just always just factor right away, but if you get 0 over 0, then consider that. Now, you got a couple options here. One, this is a sum of cubes. So I mean, one, we could use synthetic division, just like we did up above. Common tool for cubics. But you can factor it also because it's a sum of cubes. So hopefully your algebra 2 teachers will be proud of your even algebra 1. A cubed plus b cubed. It's the SOAP thing, right? Now the SOAP just tells you what the signs are, same, opposite, always positive. The rest of the pattern, hopefully you can remember, it's going to be a and it's going to be b, and it's going to be a squared and it's going to be b squared. In the middle, you multiply them together. And then same, opposite, always positive. Same, opposite, always positive. So if that helps. Now, be careful here, because I can see some people saying, oh, that's like 2ab. Nope, it's ab. You're confusing it with like a perfect square polynomial. So this also works for difference of cubes. So it's the same pattern. It's one pattern. A and B, a squared and b squared. Multiply them together. Same, opposite, always positive, right? So you might use these. That would probably speed it up. A little easier than doing synthetic. So here, we do x plus 3, x squared, plus 3x, plus 9. But same, opposite, always positive. There's the whole. Plug -3 and -3 times -3 is positive 9. Minus 3 times -3 is another plus 9. Plus 9 is 27. So, like I said, we could have done synthetic division be 1, 0, 0, 27. Take -3 out. 1, -3, -3, 9, 9, -27, 0. And here's the coefficients of the quadratic. Same answer we got, 1x squared minus 3x plus 9. So, okay. On the back, we're going to get into some other kind of new ideas. Now, so we're going to get division by 0 without it being 0 over 0. So this is a one-side limit. So this is 6 over 0 just in its, most simplest form. Can we determine this answer? What do you think? The answer is yes. Okay. So, I mean, if you divide by 0, it's undefined, but, it's blowing up like some kind of infinity, right? And you might be like, well, is it different kinds? Yeah, I mean, it could be positive infinity, it could be negative infinity. Now, here's the deal. We're not actually plugging 2 in. I mean, I know that's what we did, but we're getting close to 2, right? Getting close to 2 from the right side, okay? And this isn't a whole. This is not a whole, okay? So what you should, let's do a graph real quick of what this function looks like. This is a pretty simple rational function. It has a vertical asymptote, not a whole, at x equals 2. And then as x gets really big, this goes to 0. So as a horizontal asymptote, y equals 0. When x is like 1, this is going to be negative. We could just plug in some values. If you do x equals 1, you get -6, which is way down here. If you plug in x equals 0, you get -3. So the graph kind of looks like this. And it looks kind of like this. So as we approach 2 from the right side, you can tell from the graph that it's going to positive infinity, right? So from right side, it's going to positive infinity. Now that's looking at the picture, but we're usually not going to picture, okay? Now technically does not exist, undefined, no solution, no limit, but I need the kind of infinity. In fact, I probably want you to put a plus in front of this plus to make sure you really felt confident about it being positive infinity. But here's a different way to answer this question, okay? Instead, what we're going to do is we're going to say, so we're not actually plugging in 2, we're getting close to 2. So here's the way to kind of interpret this. A lot of times it's 0, but it's actually a really tiny number. Is it a really tiny positive number or negative number? Okay. Now think, if we're approaching 2 from the right side, then that's like, 2.00001 minus 2 is this tiny answer, but it's positive. Okay, now that's kind of not the way, I'm okay with you writing this. But a lot of times in calculus, when they want to represent some small quantities, they might use this epsilon. So you might say, oh, it's a positive small thing, and therefore it's going to positive, right? So that's how we're going to do it without the picture. So from the left side, what's happening here now? What's happening here? Well, we're pushing from the left. Okay. You might be like, well, it's 6 over 0. Okay, but is it positive 0 or negative 0? It's not really 0. It's something tiny. Now, 2 from the left would be like 1.999. Really close to 2 from the left side of 2. Well, that's going to be a negative tiny number, right? Or something like this. And that's going to be negative infinity. So it makes a difference. And on the graph, that totally makes sense. It goes to negative infinity on the left side, right? Now, just to throw something else at you, if you approach 2 superscript plus, I'm going to just change this problem. You might be like, oh, well, anytime it's plus, it's going to be positive infinity. Anytime it's a superscript negative, it's going to be negative infinity. No, it depends on how it's written. Because I could approach 2 from the right side a little bigger than 2. And if it's 2 minus x instead of x minus 2, then this is going to be a negative small quantity. And you can get negative infinity. So just be careful on those and think about what's happening. There's not like a trick I want you to memorize or anything like that. Now, these are some properties of limits. Properties would be like rules that you can use, for like there's all kinds of properties you've learned in math. These are like rules for limits. Now, if you have a limit of some expression plus some other expression, you are allowed to take the limit of the first one on its own and take the limit of the second one on its own and just add them together. Oh, well, that's nice. If there's something in front multiplying it, you could be like, okay, well, let's ignore that. Let's take the limit of the function and then multiply by 3 afterwards. Yes. How about if you got two things multiplying each other? Could we just take the limit of each of them separately and multiply the result afterwards? Yes, you can. Now, you might be surprised. What's the next one? You have division. Can we just take the limit of the top and the limit of the bottom and then divide? Yes, you can. So not a whole lot of surprises here. This is about as simple as a rule could be. Essentially, you can break limits up and do limits of parts of any limit and then do the other mathematical operations after the fact, and you will get the right answer. Okay? It would even work with, like a natural log. I'll just throw one more on here. But essentially, you can pretty much break up limits however you want. Take the limit of the inside first, and then do the outer stuff afterwards. Okay. Now for the homework, I'm going to change the homework a bit from what's written here. I decided to cut it down. I think I'm going to take out like 13 of the problems here, so nearly half. I want you to do 1 through 4 all, and then 5 to 29 odd. So I'm taking a bunch of evens out. 33 and 34. There's a few evens. This is the new updated assignment. Okay. Now, me doing that, I want you to show your work, write the problems down, box your answers, check them really well. The point of doing homework is to get better at it. And honestly, I think the biggest point of homework is to figure out what you're getting wrong still. The only way you can figure out what you're getting wrong is by doing it, checking your answer. And if you don't show your work, then it's hard for you to know what you did wrong. So if you show your work, that's also going to help you figure out what's going wrong, not that you just got it wrong, and what to fix in the future. Try the homework. Check your odds in the back of the book.